we saw what are known as the notion of simple functions, right? So before that we introduced what is known as the notion of measurable functions. And then we described a specific class of functions, measurable functions, what are known as simple measurable functions. And the most important thing that we observed here is that if yes, Dilkush.
गाड़ी हो देखना मंगला घर कौन है यार गाड़ी खंदा दियो ना
Yeah, so if omega to r bar is measurable, that means Borel measurable, then there exists a sequence. Well, in fact, not just r bar, but in fact it is 0 to infinity. It is measurable, then there exists a sequence Fn such that Fn is a simple measurable function for each n Fn greater than or equal to 0 for all n in n. Third one, they are increasing. And finally, is that they converge to f. Well, they increase. Well, before that, so yeah, they increase to f pointwise, and Fn converges to f uniformly on those sets where f is bounded. Right. So these are the things that we saw. Right. Now, yeah, so as a corollary, what is that we saw? If f and g are extended real valued positive functions, positive measurable functions, then f plus g, fg, all these are measurable. Right. So the next one is that if f from omega to c, in fact I should write it as c bar. What is c bar? Which is c union infinity. If this is Borel measurable, then we'll simply write it as and this much is enough. You don't need a c bar. If this is Borel measurable, then there exists a sequence Gn, well, Fn, consisting of simple measurable functions such that Fn converges to f pointwise. Yes. How do you show this? How do you show this? Yes, how do you show this?
We can divide like our function into real and imaginary part and apply the same.
How do you know? See, what is given is only for 0 to infinity value.
Like I can divide my function into real and imaginary part, and then real part, and then I can write into a sum of two functions like f minus or f1 minus f2 and
Right, exactly. That's right. In fact, so if f from omega to r, in fact r bar, then write f plus as max of f comma 0, and then f minus as minus of min f comma 0, right? Then f equal to f plus minus f minus. Yeah, so an exercise here is that show that f is measurable if and only if both f plus and f minus are measurable. Right. Now the proof is easy. Yes. How do you prove it? Having done all these things, or having said all these things, now everything should be easy. How do you show this? Not this exercise, the proof of the statement. This one. If f from omega to c is Borel measurable, then you get a sequence fn consisting of simple measurable functions such that fn converges to f pointwise. How do you show this? How do you show this?
Sir, as Shammi said, we will construct functions for real and imaginary value, and if two functions are simple, then there is some will be simple.
Is it done? Right? So f from, so let f from omega to c be, in fact, so it doesn't matter. Maybe I'll even write it as a, yeah, c bar. So what is c bar? C union infinity. Doesn't matter. Yeah, c bar be Borel measurable. Right. So write f as f1. Well, I'll write it as a alpha 1 times f1 plus alpha 2 times f2 plus alpha 3 times f3 plus alpha 4 times f4, where fi is from omega to 0 to infinity, 1 less than or equal to I less than or equal to 4, and alpha I belongs to C. Also, each fi is Borel measurable. Each fi is Borel measurable. Therefore, there exists sequences fn comma I, n in n, 1 less than or equal to I less than or equal to 4, such that fn comma I converges to f pointwise. Yes, this converges to f pointwise. Right, for each 1 less than or equal to I less than or equal to 4. So let me call fn as same alpha 1 fn one plus alpha 2 fn2 plus alpha 3 fn3 plus alpha 4 fn4. So then each fn is Borel measurable. Yeah, each fn is Borel measurable and fn converges to f pointwise. That's it. Right. Yes. Yeah, so next one. So before we get into this almost everywhere convergence, we need a small lemma, what is known as the pasting lemma. Correct. So let omega comma a and omega comma a dash be measurable spaces. Let E in A and F1 from E to, oh sorry, this should be omega dash, huh? Sorry, the other one should be omega dash. And F1 from E to omega dash and F2 from E complement to omega dash be functions which are measurable with respect to AE and AE complement. What is this AE and AE complement? What is this AE and AE complement?
sigma algebra is restricted to E and E complement.
Exactly right. Right. So for E in, well, you don't need that E in A. For E subset of omega, AE equal to all those A intersection with E such that A belongs to script E. Yes, so this is what is A. Right. Now define F from omega to omega dash as Fx equal to F1x if x belongs to E, F2x if x belongs to E complement. Then F is measurable. Right. So the proof, it's a one-word proof for me. The similar statement you must have seen somewhere. Do you remember? Of course, not in measure and integration. Not in this course.
Topology.
Exactly. The same pasting lemma you must have seen there, but with some minimum modification. So F is measurable. The proof, I'm just leaving it as an exercise, but you should be able to prove. If not, we'll do it in the tute. Right. Now let's go to almost everywhere convergence. Right. Yes. So now let's begin with the, well, so before we get into the definition, let me definition of what this concept is. So let me define. So let omega A mu be a measure space. Right. So we say that a property holds mu almost everywhere. Right. So in fact, so well, I should have written mu almost everywhere. So I'll simply write it as mu A dot E. So this is a very standard one. So sometimes people may even omit this mu if the measure is understood. Almost everywhere, if the property holds on a set E in A such that measure of E complement is 0. Right. That means what? All those x in omega such that x satisfies property, the measure of this set, sorry, the x doesn't satisfy the property. This set should have measure 0. Right. That means this property holds on a set whose complement is 0. Right. Fine. So let's look at a simple example. You consider this function f from 0, 1 to r given by fx equal to 1 if x belongs to q, 0 if x belongs to q complement. Of course, 0, 1. Right. So now you can notice that f is 0 almost everywhere. The function is 0 almost everywhere. In fact, almost everywhere with respect to the Lebesgue measure. M almost everywhere. So usually one writes it as almost everywhere. They don't write it as write the sum. Yes. So why is it 0 almost everywhere?
Because measure of rational numbers is 0.
Exactly. Measure of the rational numbers is 0. M star of the rational numbers is 0. And that tells us that this function is 0 almost everywhere. So this is one of the important concepts which is not available in the context of Riemann integration. So this is the one that is going to make the change. Right. Now let's get into the notion of convergence. Well, so throughout we have meha a mu. This is a measure space. Correct. Right. Now let's begin with the definition. Let Fn be a sequence of r bar valued measurable functions we say that Fn converges to f mu almost everywhere if the measure of the set, although x and omega, such that Fnx doesn't converge to fx, this set has got measure 0. So notation, in terms of notation, we'll simply write it as Fn converges to f almost everywhere. So if you want to insist on the measure, then we'll write it as Fn converges to f mu almost everywhere. If the measure is understood, we'll simply remove this mu also. Right. Let's look at an example. For each n, you let Fn from 0, 1 to r. Let Fn from 0, 1 to r be defined as Fn of x is 1 if x is an irrational. On the irrational part, define it as -1 raised to the power n if x is a rational. Right. So first thing that you can observe is that if x is an irrational number, then what will happen to fnx? Fnx is 1 for all n in n. Therefore, fnx converges to converges to 1. Right. Second thing, if x is a rational number, then fnx is -1 raised to the power n, and this doesn't converge. Which doesn't converge? Right? Fine. So now first thing is that the Lebesgue measure of q intersection with 0, 1. This is 0. Yeah, this is the third point. So therefore, fn, they converge to f almost everywhere, where f is just the constant function 1, where f is identically 1 on 0, 1. Right. Fine. Yeah. Next one. Well, let's observe some simple facts, then we should be able to. So let fn be a sequence of real valued measurable functions right. Now let me write E as all those x in omega such that fnx converges. So this set is what is known as set of convergence. Right. Now, it is known from our basic real analysis or calculus that fnx converges is equivalent to saying that this sequence is a Cauchy sequence. Yes, if and only if fnx is Cauchy. Right. Therefore, given epsilon positive, there exists n which depends on this epsilon as well as on the x, right, which is a natural number, such that modulus of fr of x minus fs of x, this is going to be less than epsilon for all r comma s bigger than or equal to n of epsilon x. Right. Right. In fact, this is equivalent to saying that modulus of f of n plus m minus fn fn plus m of x minus fn of x. This is less than epsilon for all m bigger than or equal to 1 and for all n bigger than or equal to n of epsilon x. Right. So what is this one? What is this set? What is this set? Well, let me put it in other words. So, therefore, x belongs to E if and only if, when will it belong? If and only if x belongs to, in fact, so, well, you don't need this for all n also. Even for m greater than or equal to 1, that much is actually enough. After that, after some stage, it should be very small. That's the whole idea. Right? So, x belongs to E. When will that happen? This is so, see, first thing to be observed is that this is true for all m and therefore intersection over m in n, all those y in omega such that mod f n plus m of y minus f m of f n of y. Yes, so this difference you can make it less than epsilon for some n in n and every epsilon positive. In fact, this n depends on the epsilon. So once you choose an epsilon, you get an n. That's what I've written. Right. Now again, this is equivalent to saying, now this is true for some n and n, so which depends on the chosen epsilon. So this is equivalent to saying that, so for some n, so union over n and n, intersection over m and n, all those y in omega, so that mod f of n plus m of y minus fn of y, this is less than epsilon for every epsilon positive. Yeah. So for each n, this is going to happen, right? So for some n, this is going to happen. Therefore, we have put an union. And now this is true for every epsilon positive, and therefore this is intersection over epsilon positive, union over n and n, intersection over m and n, all those y in omega, such that mod f n plus m of y minus fn of y is less than epsilon. Right. Now, instead of epsilon, I could have chosen it as 1 by k. Because of the Archimedean property, if it holds for all 1 by k, we are done. So this is same as, instead of epsilons, you put it as 1 by k. So k in n, union over n in n, intersection over m in n, all those y in omega, such that mod fn plus m of y minus fn of y, this is less than 1 by k, right? What is this set? Whatever is written within the brackets. It's the pullback of, look at fn plus m minus fn. It's the pullback of this function, pullback with respect to this function of the set minus 1 by k to 1 by k. Intersection over k in n, union over n in n, intersection over m in n. Therefore, what is E? The set of convergence is intersection over k in n, union over n in n, intersection over m in n, fn plus m minus fn, whole inverse of minus 1 by k to 1 by k. Yes. So this is the set that we are looking for. So the set that we have written here, the set of convergence is described in a different fashion. That's what it is. And the fundamental assumption, in the context is, let me now put it now. We haven't said anything before, so let me write it now. So as a result of all these, let me put it as corollary that let fn be a sequence of r bar valued Borel measurable functions defined on omega comma e. That means what? These functions are defined on omega and there is a sigma algebra on it. Right. Then the set all those x in omega such that fnx converges. That is the set of convergence. See, one thing is that this minus 1 by k to 1 by k, it is an interval and therefore it is Borel measurable. And here we are assuming that the functions fn's, each fn, they all are Borel measurable and therefore the difference fn plus m minus fn, this is Borel measurable for each n and m. And this interval is Borel measurable, the function is Borel measurable and therefore this pullback belongs to the sigma algebra an, and the sigma algebra is closed under unions and intersections, which tells us that this set, the set of convergence is measurable. Is this clear for all? This is one of the important concepts. Is this clear for all? Everyone? Please respond. Please respond to this, whether this is clear or not.
Yes, sir.
Others?
Sir, could you please explain this again?
See, if you have a sequence xn of real numbers, xn convergence is equivalent to saying that xn is a Cauchy sequence. That's what I've used. First line, fnx, it converges, is equivalent to saying that fnx is Cauchy, right? So what does it mean by Cauchy? Given epsilon positive, you get an n natural number, but it depends on the epsilon as well as the chosen point x, such that the difference between the rth term and the sth term is less than epsilon for all r and s bigger than or equal to this n, right? But this is again equivalent to saying that f of n plus m minus fn, this can be made less than epsilon for all m bigger than or equal to 1, right? Right. And therefore, once you have chosen x in E, right? So when you say that what is E, all those x in omega such that f and x converges, right? So if x is a point of convergence, that is point where f and x converges, then this is equivalent to saying that mod f of n plus m at x minus f and x, this is less than epsilon for all m bigger than or equal to 1. And therefore, so since this is true for all m, you take the intersection over m in m such that y in omega such that mod f of n plus m of y minus f n of y, this is less than epsilon for some n in n and every epsilon positive, right? Right. And therefore, this is same as saying that now, since this is true for some n, so for each, once you choose an m, you get, this should hold for, this should hold for some n. We do not know which n it is. And therefore, you take the union over n and n. We do not know, so it belongs to one of these, right? So union over n and m, same thing. Now again, this is true for every epsilon positive. Once you know that this is true for all epsilon, you take the intersection over epsilon. Now, instead of choosing all epsilon positive, it is enough to, because of the Archimedean property, it's enough to choose it and do it only for 1 by case. And that's exactly what I've done. But what is this one? All those y in omega such that mod f of n plus m minus fn less than 1 by k. This is the pullback of f of n plus m minus fn inverse of the interval minus 1 by k to 1 by k. Right? Is this clear? Atharva? So once you have understood the notion of convergence, then things should be easy. That's the whole idea. And therefore, having said all of these things, the whole point is that because now if you assume that all these are Borel measurable, this interval is Borel measurable, functions are Borel measurable, and therefore this set E is going to be a measurable set. So this is one of the important concepts. Please. Right. So I'll stop here. Yeah, I have few more results to be done, but I don't want to proceed now. I'll stop here. If you have got any doubts, please. If you don't have questions, then let me stop. Thank you.
Almost convert.
Yes.
In probability, we also have this, but we use expectation, I think, to derive the.
Can you repeat again? Sorry.
In probability, we also have almost convergence like that.
Yes, so there it is called as almost sure.
Yes, sir. But there we use expectations.
So that is integration. Expectation is integration.
Okay.